In this lecture, we're going to look at the last evolutionary computation algorithm that we're going to study in the course, and that's particle swarm optimization. We've looked at two other algorithms, the first being evolutionary algorithms, and the second NICOG optimization, which we looked at in yesterday's lecture. So the way PSO differs from the other two algorithms that we've looked at is it takes analogy from flocking or schooling or swarming behavior. So the way swarms behave and the way flocks behave and the way they work through a space, PSO tries to do the same in the search space. Like the other evolutionary computation algorithms, PSO performs optimization, so it's either trying to minimize a function or maximize a function. It's also a population-based method, so it's a multi-point search where elements of the population represent different points in the search space that we're trying to optimize. So it's a meta-heuristic like the previous two algorithms, so it's an iterative approach, and over the iterations it tries to improve an initial population. So it introduces some new terminology which we haven't come across previously. So previously, when we've employed evolutionary algorithms, we've had a population and the elements of the population represent candidate solutions. And those solutions, if you were using a genetic algorithm, were represented directly. So if you were applying a genetic algorithm to the traveling salesman problem, each element of the population represented a candidate route for the salesman to travel to get from one city to the next and to visit all the cities starting and ending at the same city. Now, here your candidate solutions are represented by a particle, and you'll see a particle is made up of a number of components. So associated with each particle are basically three different components. The first is the position of the particle, which we'll refer to as x subscript I, and I referring to the ith particle. We also have the velocity of the particle. So we're going to speak about this a little bit just now, but ideally the way the search space is searched is that these particles move through space and they move in the direction of the best known particles, the particles with the best fitness so far. And the velocity is one of the contributing factors indicating the direction in which it moves in. So the velocity we normally denote by v subscript I. And then we have a fitness value like we had with the other evolutionary algorithms and evolutionary computation in general. Each particle has a fitness value, and that fitness value we calculate using a fitness function. So if you were working with the traveling salesman problem, then the fitness value will be the distance covered by the tour, and we try to minimize that distance, so that's your objective value. If you're dealing with the examination timetabling problem, the number of constraints violated is usually your objective value, so that would be your fitness value. So like I mentioned, the whole idea with PSO is that you have different points in the search space, and these are represented by particles, but these particles actually move through the space. And they have a velocity and position that will change in each iteration, and as that position and velocity changes, the particle moves through the space. The movement is based on, like I said, the position and the velocity, but in addition to that, two other things are taken into consideration. So whenever the particle moves, its fitness is calculated as it moves to a new position, and its best known fitness up until that point in the search we refer to as p-best. So p-best is the best fitness or the position the particle was at when it obtained the best fitness so far. Similarly, we also have a global best fitness. So the global best fitness in this case would refer to the best fitness that has been found for all the particles that are moving through the space. So associated with that is the position at which that is found, and that we refer to as g-best. So different topologies can be put in place for communication between the particles, and the general topology is that all the particles communicate with each other, and the way this communication happens is by g-best. So what we mean by communicate in this context is that they actually share information, and in this case g-best is the way in which they share information. So as each particle moves through the space, its fitness will change when it moves to a new position, and that fitness value, the best value amongst all the particles at the position at which that was found, that would be the G-best value. So if we look at the PSO algorithm, like I said, with each particle I, we have three values that are associated. So we have xi, which is the position, vi, which is the velocity, and we also have the fitness, which is f of xi. In addition to that, we also have a p best of I. So the p best of I is the position at which the particles had the best fitness when it was moving through the space. So initially, these values can be initialized to 0. That's the simplest initialization. There are more complicated initializations, and this is one way in which the PSO algorithm varies what it actually uses for initialization. So you can have equations that can be used for this, you can have algorithms that can be used for it, and this is quite an active research area, is how to initialize these values. So the outer loop actually goes through, and basically what it does, it tries to find, it moves the particles through the space, and it tries to find a better optimum each time as it's moving through the space. The particles follow the best optimum particle at the moment. The termination criterion, that is problem dependent. The common termination criteria used are things like the number of iterations, that's the standard. Also a minimum error, so if you get to a point where the error for that particular function, for that particular problem domain cannot be minimized any further, then you terminate the while loop. So within the while loop, so remember the whole purpose of the while loop is to perform the process of moving the particles through space and moving those particles to a part of the search space where you can get a global optimum. The inner for loop actually traverses through the particles. So I represents the particles, and we're going from I to n. N represents the number of particles. So that's the inner for loop. And on each iteration of this loop, we're going to actually calculate the fitness, and then we're going to look at updating both the p best I value, also the g best value, and then also updating the velocity and the position of each particle. So the first step of the loop is calculating the fitness of the particle at the position it's currently in, which is xi. If that fitness value is less than the current best known position is fitness value, then that's updated. So if the fitness of xi is less than fitness of p best I, so we're looking at a minimization problem here. Obviously, if we were doing maximization, then that would be different. We'd look at it the other way around. So if that is the case, then p best I is equal to xi. So that's the update for the local position. We then do an update for the global position. So we also check to see whether if the fitness of the particle is better than the fitness for the best known position, which is g best, then we update g best. So in that case, g best is equal to xi. So those are both the updates that happen. But once those updates happen, we then have to update the velocity and the position of each particle. And that is what we're going to look at next. So different equations can be used for updating the velocity. And again, this is what gives you the different variants of PSO algorithms. So some algorithms may use one equation, another algorithm may use another equation. So we're going to look at what is a fairly standard equation. The equation for updating xi is also fairly standard. It basically takes the old xi value and updates it with the new velocity value. So the first equation we're going to look at is the equation that updates vi. So t basically refers to the iteration that we're on, so it's referring to the time. So the new velocity value is the value that's now at time t plus 1. And the first part of the equation multiplies the old velocity value by some inertia weight. Now that inertia weight is problem dependent, and there are again different ways of determining that inertia weight. So the simplest is to play with values and tune it like you would tune any other parameter. So maybe start off with the value of 1 and then decrease in intervals of 0.5. Alternatively, there are actually equations that you can actually use for W, and that also requires some initial value set in those equations. So you can work with a very simple inertia value, or you can get quite complicated. The next component of the equation is the component that's updating the velocity by taking into consideration the difference between the local best position and the current position of the particle. So you can see it's actually taking the subtraction of the best known position, p best for the particle I at time t, and it's subtracting the position of the particle xi at time t. That's multiplied by two values. And so you'll notice there's an L1 and an L2. The L2 is used in the next term of the equation. But both those values we call learning factors, and they're parameters for the PSO algorithm. And these are set like you tune any parameter for your GA, like population size, application rates, crossover rates, etc. These are tuned, and they multiply by R1, you'll see an R2 in the next term. And these are random values in the range 0 to 1. So it's just, it adds some randomness and it adds some noise. So the second term of that equation is actually updating the velocity, taking into consideration the difference between the best known position for that particle and the current position for the particle. The last term in that equation, which is multiplying L2 by R2, it's then looking at updating or taking into consideration the difference between G best and the current position of the particle when updating the velocity. So that's the last part of the equation. So once we've worked out the new velocity equation or the new velocity value, that value is then used to update the new position for the particle. So if we look at the position update equation, so if we look at the position at time t plus 1, it's the old position at time t times the velocity at times t plus 1, plus the velocity at times t plus 1, which is calculated by equation 1. So these are the two equations that are generally used, but like I said, you can have various velocity equations, and that's what gives you the different variants of PSO algorithms. So when you implemented the genetic algorithm for Sudoku in assignment 2, the one thing that you learned was the whole idea of parameter tuning. So the parameters for different aspects or different, the values for different parameters of the algorithm linked to different aspects, there isn't a set value. These values are problem dependent, so things like population size, chromosome length, mutation rate, application, crossover rate, tournament size. These values you had to play with and tune. So similarly, when it comes to PSO, there are certain parameters that need to be tuned. So the first parameter is synonymous to your population size, so it's the number of particles. Vmax is a very interesting parameter. And so if you remember, we have different equations for updating the velocity. What happens if you get too high a velocity? It causes quick convergence of the particles. And if there's a quick convergence of the particles, they converge too quickly, or they prevent convergence from happening altogether, and then you miss your global optimum. So for that reason, you want to control the values of velocity. So if they get too high, you could not converge at all for each particle. So for that reason, a Vmax is set. That's also a parameter value. Again, Vmax can be a simple value that's randomly chosen, or you can actually have equations that are used for Vmax. So what happens is if the velocity calculated for any particle at any time exceeds Vmax, then Vmax replaces that velocity. We spoke about the inertia W or the inertia weight W. That again, you can randomly choose values and you can play with values given different intervals, or alternatively, you can use quite a complicated equation to give you an initial inertia value. L1 and L2 are learning factors, so these are also parameters that need to be set. And then lastly, like with your GA, you have some termination criterion, and common criterion used are things like the maximum number of iterations and minimum error, etc. So like we had with the ant colonization algorithm, we have a similar situation with PSO. There isn't one set PSO algorithm. So you can have different PSO algorithms, and they differ with respect to different aspects of the PSO algorithms. So one of the main ways in which it can differ is how you actually create initial values for both the positions and the velocities. Also the update rules, so the rules for updating both the local and global position after the swarm is updated. So that would be one thing that could happen. You could do it in the current algorithm. It happens while the swarm is being updated, but you could also do it after the swarm is updated. So you could change the update rule from the standard rule. And then, of course, the velocity equation, how you update that. That will give you different variants of the PSO algorithm. So that brings us to the end of PSO. It also brings us to the end of evolutionary computation. And that's the last lecture for the course. The final lecture on Monday will just be feedback for test 2. And we'll have a session where you can ask any questions for test 2 on Blackboard on Monday. So I'm going to stop there for today's lecture.